Other questions? Okay, so I'll start. So far we have been studying how matter behaves in the presence of gravity, right? Which may involve particle-like objects or electromagnetic field. Okay. But today we will ask the reverse question, okay, that what produces a gravitational field? If you have some matter distribution, okay, what kind of gravitational field is produced? Okay. So question that we want to study today is, what is the equation that determines the metric? Okay. And here you cannot give a fully systematic derivation, okay, because the equivalence of principle is of not of much use. Okay. But we will try to see how far we can go, right? I mean, we will try to justify the equation as much as possible. Okay, but there will certainly be some guesswork involved. So the first thing we'll assume that these equations can somehow be derived from an action. Okay, we don't know what the action is, but let's suppose that the equation is derived from an action principle. Okay, an action principle means that you write down some action, okay, which is an integral of a Lagrangian density, okay, and then the equations of motion are derived by saying that the first order variation of that action should be 0. Okay, that's the usual way we use action principle, right? Just like in classical mechanics. This is familiar to all of you. Classical mechanics, how you derive Euler-Lagrange equation, for example, right? So it's similar. So let's assume that there is some action. Okay. And then we also assume that it's general coordinate invariant on a general coordinate transformation. Okay. So we'll take the action to have a sum of two terms. Okay. One term is purely a function of the metric. Okay, let me write this. LG plus so these, okay, so let me explain these various things. Why square root of minus determinant G? Okay. And so the point is that d4x is not equal to d4x prime under general coordinate transformation, right? Because we saw that there is a Jacobian involved, right? d4x, when we make a general coordinate transformation, there will be a Jacobian that is involved in this. Okay. But this combination, determinant of G is also not equal to determinant of G prime, because G, as we saw, is some product of a matrix times original G, the G prime times the transpose of the matrix. So determinant G and determinant G prime are not equal. But I'll leave it an exercise to show, this is a simple exercise, that this combination is general coordinate invariant. Okay, namely whatever determinant you get in changing variable from x to x prime, okay, is exactly cancelled by the determinant that you get from changing G to G prime. Okay, that's why we write it this way. So once we know that this is general coordinate invariant, then we can say that this must also be general coordinate invariant. So this must be some scalar constructed from metric. This one also has similar structure. So this is general coordinate invariant. So this is also a scalar. But this is scalar constructed from other variables and metric. Constructed. Yes, it could be a function of g and derivatives of g, right? We are not putting any constant on what kind of function it is. Okay, but it doesn't involve anything else other than g mu. So this is a scalar which is constructed from the metric and other degrees of freedom. Okay, like x mu, f mu nu, etc. Okay, the particle trajectories. So this, if you remember, in the case of electromagnetism, right, this was the analog of f mu nu, right? Electromagnetic field. This one part depends only on the electromagnetic field, right? The other part gives the coupling of the electromagnetic field to matter, for example, right? A mu j mu tau. Here we will also allow dependence on metric because we will see that it's not possible in general to write a general coordinate invariant action without using the metric. Okay. Nevertheless, this has the property that if all the other degrees of freedom are set to 0, right? When there is no x, there are no particles, there is no electromagnetic field, then this should vanish. Right? So you can think of this as what will give the source term in the equation of motion. Okay, the j mu. This will give the analog of the j mu term. Because this part is general coordinate invariant, right? So if you want the action to be general coordinate invariant, right, then this shouldn't transform the general coordinate transform. So okay, just x to x prime, right? The argument will change and transform. So that's why you took it to be a scalar. Exactly, right? So if there is general coordinate invariant action, that's saying that this is what your way to get a general coordinate invariant action. Capital X is the x of u, that xn of u. Put it is xn of xn mu, right? Of u. This is particle trajectories. Right? Because our goal is to understand how, for example, a particle trajectory affects gives rise to metric, right? So this will provide the analog of the source, right? Even in the case of electromagnetism, right? There's an a mu times j mu, and j mu was written in terms of particle trajectories, right? So you have the analog of that term. Yeah. So now, if you want to derive the equation of motion for the metric, or g mu, this should be obtained from delta s equal to 0 under arbitrary delta g mu nu. Okay, you vary g mu nu to delta g mu nu x, and the change in the action should be 0 to first order. That's the extremization principle. And here you will also assume that the variation that you are taking vanishes at the boundaries, so that you don't have to worry about boundary terms. So you can always do integration by parts. So given this, what will be the general structure of this? Right? So delta S. So here, when you vary with respect to the metric, right, this will have the form integral square root of minus determinant G. This also has to be varied. Let me call it capital G mu. So this is something made of metric. Right? Because delta G, whatever is the coefficient of delta G mu, I am calling capital G. And then this term will have integral square root of minus determinant G d4x delta G mu nu right? But I could have written d4x at the beginning. Is this clear? Yes, yes. Yeah. So this delta G, when you vary the delta G, you have to vary the determinant of G also, right? After you vary everything, I'm saying that you just pull out a factor of square root of minus determinant G. Whatever is left, I call this. Okay, so when you vary, we have to vary everything, right? This as well as this. Boundary terms will go away because of this delta G mu nu I've taken to vanish at the boundary, right? We take delta G mu nu to be non-zero only in a some say a finite region, right? Outside that it is zero, so the boundary terms you can ignore. Some tensor at this point. Well, I just factor it out. If there is something not factored out, that's inside this, right? That's all we are saying. That we just pull out root minus determinant G, and whatever is there, you call this. Okay, and the point is that because we know that S is a scalar, so the variation of S should also be a scalar. It should be invariant on a general coordinate transformation, right? We know that whatever it is, this combination is a tensor, is a scalar, right? And hence this is a tensor, right? So even after you do all that, right, vary determinant square root of minus determinant G, etc. After that, when you pull out square root of minus determinant G, right, whatever is left should be a scalar under general coordinate transformation, because this has to be invariant. Okay, in the intermediate stage, of course, you will get many things, right? But at the end, this should be a scalar. So this then tells us that the equation of motion should take the form G mu nu equal to minus H mu nu. Because the coefficient of delta G mu nu has to vanish. This can be completely arbitrary. Then we can take this to be localized in a given point, for example, delta function. Right? So the coefficient should vanish. So some of these should vanish. So this is the general structure of the equation that we expect. Right? Left hand side contains only metric. Okay? Right hand side contains the sources. It may also contain the metric, but predominantly it's the analog of the J mu, right? And this is the analog of the left hand side of the Maxwell's equation. Is clear? No, I'm not assuming any such thing. LM could contain, for example, the coupling of the Riemann tensor to the matter.
So it can contain derivatives of G as well.
Yes, exactly. All of these, LM and this can contain derivatives of G. Yeah, so you are not making any such assumption. Right? All you are saying is that these terms should vanish when the source terms all go away. Right? If there are no particles and no electromagnetic field, right, then this will vanish. Right? So in the absence of source, the equation of motion should be g mu nu equal to 0. Yes, anything. It can have arbitrary number of derivatives, right? I mean, LM can have a term like this, for example, R mu nu rho sigma, F mu nu, F rho sigma. Right? Well, how do you know usually, right? We are just trying to make the most general possible configuration, right? So after that, we will have to see how to make connection with what we usually do, right? But right now, we are trying to say that let's try to be completely general and see what kind of structure we expect of the equations of motion, right? And what we are saying is that the structure we expect is this. So the only thing that we demand of LM, as I said, is when all the sources go away, LM should be 0, right? Because that term should have been included already in this. Okay, if there is a term, for example, R mu nu rho sigma, R mu nu rho sigma. This part will include in LG. Okay, because this term there are source terms here. That's the only thing I have used in this split. Okay, otherwise I am not saying anything. Is it clear? So our goal will be to try to determine or guess what are G mu nu and what is our H mu nu. Right? Both left and right hand side of Einstein's equation, we have to find somehow, right? At least use some physical insight to figure out what these could be. Is it clear?
So this is like whatever the evolution of the electric field that is governed by all sort of sources, electromagnetic sources, that also can affect the.
Exactly. Right? Right now we have to allow everything, right? We don't know that electromagnetic sources do not affect metric, right? We are saying let's try to be most general. Whatever governs the equation of the metric would depend on all sources, right? Electromagnetic field, the x's, metric itself can affect, right? But that effect will be included in this. No, we are assuming that anything that requires things other than the metric could contribute. Yeah, if there is a charge affects, right, then it will be included here. It's charge of some particle, right? So basically it will affect to the x's. Right? So at this stage you are not assuming anything. As of now, yes, right? So this is a very general structure, right? You have to do a little better, right? Because just writing this is not very helpful, right? Okay. And the other thing we'll say is that these are tensors, right? Because these should be scalars, right? Delta G is a tensor, so these should be tensors. So 2 rank 2 0 tensors is what we are looking for, right? Both the left hand side and the right hand side. So next thing we'll try to do is to find the analog of that condition that we had seen earlier, that if you remember for the Maxwell field, right? Because of gauge invariance, we know that if you take the divergence, 4 divergence of the left hand side, it's identically 0. Right? That's basically for the Maxwell, let me remind you, for the Maxwell, it's basically the statement that if you take this is 0. Yeah, this is 0 because this is antisymmetric, this is symmetric, this is antisymmetric. Okay? That's what you saw earlier. And this in turn means that this is 0. Because if the left hand side is 0, then right hand side better be 0, right? So what we are going to try to find now, okay, is the analog of this statement, right? Because that will put some constant on what this G and H are. Is that clear? Now, if you recall the way we derive this, of course, if once somebody gives you, you can easily check, right? But we gave a general derivation, right? That didn't require that we start with Maxwell action. Okay, that only required that we start with an action that depends only on F mu, right? And just from gauge invariance, we could prove this, that whatever is in the left hand side, even if this is not the correct left hand side, right, which would not be if the action is not the Maxwell action, but whatever is the left hand side, right, will have this property that the divergence of that should vanish. Right? We said that let's take the mu, the variation with respect to mu's, or let's call it E upper mu. Okay? That E upper mu should have vanishing four divergence, right? Just from the gauge invariance. So we are going to try to find an analog of that statement here, right? What we expect these to satisfy. Is this clear? Yes, gauge invariance implies charge conservation. Yes, because gauge invariance tells us that the divergence of the equation should be 0. And because the equation of motion is E mu equal to J mu, right, it also tells us that the divergence of J mu must be 0.
But you have some sort of a Lagrangian for the that is different from the.
As long as it's made of F mu nu.
Yes, but you expect the first statement to be true, but may not be true that del
Well, that's the structure of the equation, right? They look at this. There, all that we had is the first part was some arbitrary function of F mu nu, right? Gauge invariant function, and the second part was the coupling. We define J mu that way, right?
See, you're saying that there will be some sort of source term on the right.
Exactly.
And the divergence of the source term will be 0 from gauge.
Exactly, right? Even if the actual theory is not Maxwell theory, right? As long as you have gauge invariance, right? And whatever Lagrangian you are using, if it's made of F mu nu, right, then it has, of course, has gauge invariance, right? F mu nu doesn't transform. Right? That is good enough to make that conclusion.
It's kind of precise. The first equation may not be the same, but we'll always have something like the second equation.
Yeah, well, first equation will also be the same. It will not be the exactly same as this, but there'll be something like this. E mu is whatever is on the right hand side of on the left hand side of the Maxwell equation. Right? E mu is what you get by varying just the part of the action that involves only the gauge fields. Right? And then because if the equation is E mu equal to J mu, right, this must also hold. Is that clear? So we are going to try to find the analog of that statement in this case. Okay. And the role of gauge invariance in this case will be played by general coordinate invariance. Okay, so we will now try to see how we can use general coordinate invariance to get some condition on the left hand side. See, left hand side comes first because that's where, like in Maxwell's equation, right? This came first, and then that implied this. Mm.
We will always have some kind of
Condition like this, exactly. Right? I mean, it should be clear also explicitly from Maxwell, the derivation that I gave for Maxwell, right? Because all he said that if the particular delta mu is a gauge transformation, then the result should vanish identically, right? That's all he said, and that's what gave this condition. Right? We are going to follow exactly the same principle to see what the condition we can get here. So let's look at gauge transformations or general coordinate transformations. We have G mu nu of x as This is the general variation. Now, because we will be applying it, right? So the idea is that we will take the left hand side, right? Delta G mu nu H mu nu. And then, sorry, delta, the left hand side of first equation, delta G mu nu capital G mu nu. Okay. On the second one, it's a little more tricky because on the second one, if you want to apply this, right, that's also general coordinate invariance. But there, the general coordinate transformation also acts on the x mu's and the a mu's and so on, right? So it's more difficult, right? Because you may not a priori know what fields you have in the problem or what other degrees of freedom you have. For the first one, there is no problem, right? Everything is made of metric, and for metric, we know clearly what the general coordinate transformation rules are. Okay. But we have infinitesimal partition, right? Delta, that equation is valid to only first order in delta G, right? The first variation should give you 0. So if we want to apply the general coordinate transformation on that, we have to look at infinitesimal version of general coordinate transformation, okay, where x prime and x differ by small amount. Okay, but that we can work out because of course you have the finite version. So let's suppose x prime of rho to be x rho plus epsilon times some xi rho of x. Some function, arbitrary, epsilon is a small parameter, and there is some arbitrary set of functions. Then this will be delta rho mu plus epsilon right. We just take a derivative with respect to x mu. Okay, and now we are going to substitute that. So you get G mu nu as and finally here we are going to expand it out as G prime rho sigma of x plus order epsilon square terms you don't care. Right, I want to relate G mu nu of x to G prime mu nu of x because that's the change, right? Because G prime mu nu argument has gone from x to x prime, right? I just Taylor series expand around x. Okay. So now we just expand it out and keep only terms of order epsilon, the term up to order epsilon. So the first term is the product of these, right? That gives you G prime mu nu of x. So that basically says that to order epsilon to the 0, G prime and G are the same, right? Because we are doing infinitesimal coordinate transformation. Right? If you said epsilon equal to 0, you are not doing anything. Here? Okay, it was x prime, right? But I wrote x prime as x plus this, right? And I'm Taylor series expanding that object. Exactly, yeah. So delta G will be calculated at the same point. Right? That will be our definition of delta G. The difference between G prime and G. So you have this plus epsilon okay, the rho will become, sorry, sigma will become equal to nu. Right? Because from here you pick the delta sigma nu term, then there will be epsilon Now rho will become mu. So mu sigma plus is this clear? I just expanded this product, right, and kept only linear terms in epsilon, right? So in the first term, I have picked the epsilon term from here, but this delta and g prime from here. In the second term, I picked the epsilon term from here, but delta and g prime from here. And in the third term, I picked epsilon term from here and then delta and delta. Second term sigma will be rho here. Oh, Zyro, thank you. Yes. Yeah, because I'm picking this term. Okay. So let me just write this in a clean way. Okay. So I can write g prime mu nu of x. I put to everything on the other side as g mu nu of x minus epsilon all this. Okay. But inside this, what I'll do, okay, because you already have order epsilon, right? I can replace g prime by g because g prime and g differ by order epsilon terms, right? We are not keeping track of order epsilon square terms anyway, right? So I can just replace g prime by g. So I'll write this as minus so these all our arguments are all x. Where x and x prime now just differ by order epsilon anyway. Okay, plus order epsilon square, you don't care. Is this clear? Now I'll leave it an exercise to show that this is given by g mu nu of x minus okay, maybe I write yeah epsilon. I write one more step and then I'll there's epsilon. The first will be g rho nu d mu Zyro plus g mu sigma d mu xi sigma. Okay, this is first step, and then I can write this as g mu nu of x okay, where indices are raised and lowered by sorry, I knew. Okay, so let me explain what I did here. So this term I am replacing by a covariant derivative. So obviously I am making some error, right? Because the covariant derivative has a gamma terms. Similarly, this term I am replacing by a covariant derivative. So it has, again, there are some errors. This has a gamma term. And the idea is to show that those gamma terms are precisely these. Right? Gamma we know in terms of derivatives are a metric, right? You have to just substitute and manipulate to show that the extra gamma terms that you get here are exactly coming from here. Is it clear? Okay, so now we are going to make use of this fact that the action was general coordinate invariant. So if we replace delta G mu nu by this, then the result should be identically 0. Right? It's the same kind of argument that we gave last time, right? The action was invariant on a gauge transformation, right? We have a formula for explicit variation under arbitrary delta mu, right? So if we now substitute for delta mu, the gauge transformation block, then the variation should be identically 0. That was the logic, right? We start from a gauge invariant action, right? The expression for delta S is written as a mu times m e mu, right? And now original action was gauge invariant, right? So obviously under delta mu equal to d mu lambda, the derivative of lambda, you should get 0, right? And that's how you are explicitly substituting on the right hand side. So from this we conclude that integral d4x square root of minus determinant g is this clear? Okay, let me again explain the logic. So what we said is delta of integral here there is no general coordinate invariance involved. This was the definition of capital G mu, right? That under an arbitrary variation of the metric, you should get this, right? That's how you define capital G mu. So this is statement number 1. Statement number 2 is the delta of integral square root of minus determinant g d4x lg is identically 0 if delta J mu nu is minus epsilon d mu xi nu plus d mu xi nu. Why? Because this is general coordinate invariant by definition, right? And this is just a particular version of general coordinate invariance, right? Infinitesimal general coordinate invariance changes g to this by this. So if we substitute for delta g, this expression, you should get identically 0. Is that clear? Now the third step that we had carried out for electromagnetism was that you have to integrate by parts, right? Because let me remind you, what we had gotten for electromagnetism was that integral right? This is the analog of this statement that we have arrived at here. But then we said that we can integrate by parts and write it as integral lambda, okay, ignoring boundary terms, assuming the lambda vanishes at the boundary. Right? And then we say that because it's true for arbitrary lambda, right, this must vanish. Okay, so this integration by parts is what we have to do here, right? Because we want a statement on G mu nu. Okay. Okay, so let me stop here. So this is the equation that we have gotten. So what we would like to do is to somehow make these derivatives act on this, right? Oh, I should have said another thing, that G mu nu can be always chosen to be symmetric. Look at the definition of G mu nu, right? It's giving delta G mu nu times G mu nu, right? If there's an antisymmetric part of G mu nu, it doesn't contribute anything. Right? So we'll take capital G mu nu to be symmetric.
The second point that you have
Yes.
means that the variation of G mu nu cannot be truly arbitrary. Right? There are certain null things. I mean, we did G mu, we have to be careful that it's not a general coordinate.
No. If it is general coordinate transformation, then the left hand side should identically be 0. Right? Otherwise, this is not, we are not claiming that this is 0. If you take an arbitrary variation of delta G mu nu, it's not 0, right?
Specific variation that is equivalent to a general coordinate transformation.
For that, it is identically 0. Yes, and you are going to use that to get some condition on this capital G mu nu. Okay, so now I'm going to give you another exercise, which is a little more difficult, but it's just algebra, which is that we see what is the difficulty in doing integration by parts. Right? This has one ordinary derivative. Right? That ordinary derivative we can integrate by parts. Right? But one of the problem is that it, of course, acts on this, but it also acts on this square root of minus determinant G. Right? You have to take that into account. Okay, it will produce some factor. The other problem is that this has gamma. Right? It's not just ordinary derivative, right? This is gamma. Right? So what is the meaning of integration of parts with gamma, right? It just is there. The point is all of these effects, right, compensate each other. And what one can show is that this equation actually implies that integral d4x square root of minus determinant G. So I should have, I can just to simplify things, I can just say that I can drop this. I can just drop this and multiply this by a factor of 2. Right? Because this is symmetric. Right? So it doesn't matter if you add this or not. It's the same result. So the statement is that this is given by 2. There's a minus sign, right? Because when you take 2 integration of parts, you get a minus sign. Namely, these are some gamma. There's some gamma factors, right? This one has different kind of gamma factor, right? Because it's acting on G mu nu, right? A rank 2 tensor. Obviously, this has different structure. So the gammas are different, right? The other thing is that this derivative, when you do integration of parts, it also acts on this. Those effects all cancel, okay, and give this exact equality. Is this clear? And so for that, you basically have to use this fact that's the determinant of a matrix. You can write as determinant of so this is e to the trace log of the matrix, and then when you take the log, you get trace of M inverse okay, which basically means that is the same as determinant of M times trace of M inverse okay, this is a general result about the determinant of a matrix, symmetric matrix. Okay, and then you have to apply it for M equal to G. Okay, so you will get a determinant of G, and then you get an extra trace of G inverse times the derivative of G. Right? Is those derivatives of G which basically will compensate for the gamma, right? Because gammas involve derivatives of G. Right? And what you can show is that by they all reorganize themselves to give this cancel the gammas, and you can just do integration by parts.
parts we don't, we cannot apply it to the covariant derivative.
Exactly. Yeah. So that's the point. But it's as if you can apply it to covariant derivative, right? When you apply to partial derivative, right, you get extra factor from square root of minus determinant g, right? But you also have extra gammas, right? The gamma on this side is not the same as the gamma on this side, right? So that difference exactly cancels the fact that the derivative acts on this, right? It's algebra, but this is something that we should do, right? So this is an exercise. So this step is an exercise that you can do, and this is a general principle. So the point is that as long as the measure involves d4x times square root of minus determinant g, which is the general coordinate invariant measure, you can do integration of parts with the covariant derivatives as if they are ordinary derivatives. Okay, so this is general statement, right? And this is just a special case of the general statement. You probably can, except that you are doing an integral, right? So maybe locally, point by point, you can do it, but it's a little dangerous argument, right? So I'd say it's best to just do it, right? Yeah, do the calculation and check. But there must be a way to, cook up an argument based on this, right? You just divide this into small cells, and then inside each cell you go to flat coordinate system and apply this. Okay, and then you have to make sure that the boundary terms from each cells, the cells just cancel each other, right? Yeah, so I think you can do it, but one has to be somewhat more careful. Is this clear? Okay, so now at least you have got something, right? Because this has to vanish for arbitrary xi nu. Because this was an arbitrary local coordinate general coordinate transformation, right? Infinitesimal general coordinate transformation. So if this has to vanish for arbitrary xi nu, then this must be 0. This is the analog of the equation that we got for the Maxwell case, right? The d mu of E mu should be 0. So let me summarize what we have gotten. So we have gotten that the equation of motion of the metric is of the form g mu nu equal to minus h mu nu. Okay, this is the first statement. The second statement is what we just saw, is that d mu g mu nu must vanish. And this means that d mu h mu nu must also vanish. By consistency. For consistency. The danger is that h mu also contains other variables, right? X mu and the f mu, right? So they also vary. Under general coordinate transformation, right, they will also vary. That we have not taken into account, right? Because we have not committed ourselves to what kind of other fields are present. But that need not be 0 for the right hand side.
also has some terms related to the metric, right?
But those were all took into account, right? By definition, right? The variation of the action, right? Everything has been taken into account in the LG, right? Whatever could vary under general coordinate transformation has been taken into account, right? On the LM side, right? We have not taken into account every possible variation, right? Because metric variation you can take into account by this same logic, right? But the x mu and f mu nu, right? If we knew what the structure is, we could have taken them into account, right? But that we haven't done. Okay, but there is something that we can say, right? Which is the following: that on the right hand side, the variation of whatever it is, right? Whatever field it is, should vanish when equation of motion of that field is satisfied. That's the statement, right? That's a because equation of motion is that the first variation should vanish, right? So imagine that we don't know what the dependence on those variables are, right? So we are missing, if we try to apply this logic, right, on the right hand side, we will be missing terms which are the effect of first variation of those other things, right, multiplied by whatever the general coordinate transformation those fields are. As long as equations of motion of those other fields are valid, right, then those variations should vanish, right? So on the right hand side, the statement is a little more complex. It must vanish for consistency, but it will vanish only when equation of motion for all the other things are valid, right? On the left hand side is identically valid. On the right hand side, it's not identically valid, right? It should be valid only when all the equations of motion are satisfied. And we will see an example of that in a few minutes.
That is to this kind of argument of
Left hand side.
right hand side. The mu of h mu will vanish only when the other fields are following.
Exactly. Yeah, because this is for consistency, and consistency can be demanded only when everything satisfies the equation, right? That is the equation of a metric, right? But what you are saying here is that this part, d mu h mu nu equal to 0, will be valid only when the equations of motion for all the other fields are also satisfied, right? This left hand side, right? The statement that d mu g mu nu should vanish doesn't require that the metric should satisfy its equation of motion, right? Because we never use equation of motion, right? We just said that the variation of the action is delta g mu nu times capital G mu nu, right? Just based on that, we concluded that capital G mu nu has this property, right? So on the left hand side has to be valid without using any equation of motion. Okay, that is not true for the right hand side because of the fact that you have not taken into account other variations of the other fields or degrees of freedom.
But the first equation of motion equality will only be valid when G mu is valid without the first statement being valid. Right?
Yes, exactly. That's right. This is valid without the first statement.
Yes. If the first statement is valid, then
the third one should be valid for consistency, right? But we will see that the validity of third one will also depend on the h mu nu being constructed out of variables which satisfy their equation. Because we didn't, if you look at the derivation, we never use equation of motion. All we said is that the delta G mu, the capital G mu nu is defined as the coefficient of delta G mu nu when you vary LG, right? We didn't say that the variation has to vanish. Right? That's why the second line doesn't really, it's completely independent of the first line.
seeing that this action principle has been applied incomplete in some sense because we have not considered the variation of the
Yeah, the full action. So because it's not incomplete, we have not gotten all the equations. That's all it says. The other equations you have already seen. Last time you already saw how to get the equations of motion for the other fields, right? Okay.
So this is an equation in addition to the equation we already have.
Exactly. And for consistency, those equations of motion must be obtained by varying the same action with respect to those fields, those variables, right? X mu and A mu. Okay, we didn't derive them from action principle, but if there is an action principle, then all the equations must come out by varying the action. Okay.
This thing just requires that we consider the equation of motion corresponding.
this last thing.
Yeah.
Yeah, last thing requires that we consider just it was a consequence of just considering equation of motion for GBU, right? But this is a consistency condition, right? So we don't. I mean, why should we expect that things will be consistent unless you have imposed all the equations? It just says that okay, we have this equation, right? Suppose the d mu g mu is equal to 0, and d mu h mu is not equal to 0. Then there's a problem, right?
Yeah.
Okay. So there is a problem if d mu h mu is not 0.
HB will have fields like F and X, right?
Yes.
And those might not be following the equation.
Then we don't expect inconsistency. That's the point.
Oh, okay.
Right? I mean, the third one, right, is not derived from anything, but we are saying that if everything is consistent, if you have to get any solution at all, right, it better be the third one is true. Right? If you don't satisfy the if the sources, right, don't satisfy the equation of motion, then you may not be able to solve this equation, right? What guarantees that you have any solution at all of the first equation?
The thing is, why are not variations of X and F not coming?
No, they will come. I mean, if you want to derive the equation of motion for those from the same action, then they will come. We have not just done it, right? Because we studied the equation of motion for X and F last time, but there we didn't use action principle. We could use action principle, and we could derive those equations also from the same action, right? But whatever it is, what this is saying, right? Let's look at the third statement a little more carefully. That we know that the form of the metric equation is this. Okay? We know that this is 0 identically. Okay. Now, what is the third equation telling you? Right? That if d mu h mu is not 0, you will never find a solution. Right? Which is okay. Maybe those equations have no solution, right? But that's not the kind of theory you're looking for, right? So if you want solutions, then it better be that d mu h mu is 0. Right? And this is tightly constant, and as long as h mu, that h mu part is also derived from, as long as the equations of motion for the other objects are also derived from an action, we expect a consistent theory. Right?
Let's say we treat other fields as a non-analytic, then we have for consistency condition we have to impose that.
Exactly. Exactly.
But at discussion, if we start with this action,
Yes.
then we'll arrive at this kind of a
Which second or third? Second.
third one.
Third one. Yeah. So that's what I'm saying. Suppose h mu are non-dynamic. H mu are something given to us. And I tell you, okay, go and solve for the metric. You may not be able to find a solution. Right? That's what the third equation is saying. That unless d mu h mu equal to 0, you know without doing any calculation that you are never going to find a solution.
What I'm saying is, first and second equation that you said.
Yes.
If we have, let's say we have an action where the metric is coupled to something, other fields and metric itself. So let's say we vary the action. So up there, so we got delta G mu G mu, right? So under the situation where the variation is a general coordinate transformation, we expect this kind of d mu of total covariant derivative
Should be 0. Yeah.
Type be 0. But if we start with this action, we will end up with something like d mu minus plus d mu h.
Oh, I'm saying that individually LG, that first term and the second term are general coordinate invariant.
Yes.
Right?
Yes.
So I can apply the fact that the general first term itself is general coordinate invariant, right?
Yeah, but both of them are expected to be general coordinate.
Yes. But the second one, right? The reason that we are not being able to apply that argument directly is because under general coordinate transforms, other things also transform. Right? X transforms, A mu transforms, right? So unless you put those in, you cannot get that result, right?
We are only safe when we have let's say scalars.
Scalars also transform the general coordinate transformation, right? Because phi of x goes to phi of x prime. Phi prime of x prime is phi of x, right? So that part of the transformation is still there. But so what I was saying is that so this statement, right, you can think of it in the following way. One is that imagine that the source h mu is provided by some background, right? The other part that we are saying, right, x and a somebody gives me. Okay, I don't know where it came from. If that is the situation, then unless that whatever somebody has given me, a and x, if that doesn't satisfy this, we'll never get a solution. Right? That is a statement. That is what I have said so far, right? Well, okay. Sources don't have to satisfy any condition, right? They have to only satisfy the equation of motion. Because if they satisfy the equation of motion, then we argued that the first variation is zero of the under those is zero anyway, right? Then this equation will be valid automatically, right? So as long as the sources satisfy the equation of motion, right, and the equations of motion are derived from the same action, then we are guaranteed that this will be true. If we don't say, if you don't care that the sources satisfy an equation of motion, you decide that okay, these are my sources. I give you this, and then you find the solution. Right? Then you have to ensure that this condition is satisfied. Right? Otherwise, nobody will find a solution.
It's the same statement that continuity conservation of charge follows from the maximum.
Exactly. Yeah. Exactly. Except that there is a slight difference. The continuity equation, right, didn't require that equations of motion are satisfied. Continuity equations are derived, right? If you remember, the x equation are never needed, right? That will not be the case here, and we will understand why, right? Because here the sources will be the energies, and unlike charge, right, which is always conserved, irrespective of whether equation of motion is satisfied or not, energy is conserved only when equation of motion is satisfied. Yeah, that's the reason why you need that the equation of motion is satisfied. But that the general logic that I gave, right, it follows from this observation. That in general, the variation of the second term, right, is zero under arbitrary variation of things if the equations of motion are satisfied. Right? Because that's the meaning of equation of motion. Right? All force variations should be zero. So if you have already satisfied equation of motion, then the fact that you are not taking into account the general coordinate transformation of those other things doesn't matter, because those variations, the first variation is zero anyway, right? So as long as the equation of motion are satisfied, this condition should be automatic. But if the equations of motion are not satisfied, right, then you have to make sure that this condition is true.
So this procedure in general is valid for gauge theories, that we take a part of the Lagrangian which is dependent exclusively on the gauge,
Yes.
which is G in this case, and we take its variation, which is exclusively dependent on G and is gauge invariant. These two conditions.
Yes, exactly.
Which gave us this identity.
Exactly. That's it. Exactly. Yeah, it's true for general gauge theories. Indeed. Well, not really, because here you're talking about the equation for the metric, right? This one, okay, you are asking if this one depends on the equation that the particle satisfying equation of motion, and indeed you will see that unless the particles move on a geodesic, right, this equation will not be satisfied. In a background metric that is there, yes. Right? It's a coupled set of equations. Right? G mu nu determines the particle motion and particle motion determines G. Right? So in that background, the particle has to move in a geodesic. Okay, so now let's try to be more specific, determine what these things are. So G mu nu now just from the general principle, you have gotten whatever you think, right? You have to now try to use some insights. Okay. So here you are going to use the insight that in appropriate limit, it should reduce to Newton's law. Okay. So Newton's law for gravity basically is this. Is a gravitational potential is proportional to mass density. Right. So left hand side G mu nu should have something to do with this, and the right hand side should have something to do with the mass density. This is the source, and this is the gravitational field. Now, what we can guess from here is we have already seen that V is directly related to H00, right? Up to some proportionality, just by taking the weak field limit. So the left hand side should involve some second derivative of H00. So the important point here is that it should involve two derivatives. Okay, that's so you will now assume that this G mu nu must be constructed out of two derivatives. Okay, because this has two derivatives, right? Newton's law didn't have four derivatives. Now this, of course, could break down. You can say, okay, maybe there is a term on the left hand side, right? It has four derivatives, but the coefficient is small. Right? That you cannot rule out. Okay, so that's why it's not a derivation. Okay, what I'm going to give, it's only that minimal thing that you can do to reproduce Newton's laws. So G mu nu has to be constructed from two derivatives, right? This is a tensor. So what tensor can you construct out of two derivatives of a matrix? Riemann tensor, right? Riemann tensor, but you have to have only two index, right? It's a rank 2 0. Ricci tensor. So R mu nu you can construct, right? What else can you get? Two derivatives. G mu nu has no derivative, right? You are almost right, but G mu nu is R, right? So R times G mu nu. Right? Nothing else you can get out of Riemann tensor, right? You can these things have more derivatives, right? You can of course construct tensors. Yeah, it is only tensor, but that we did the counting, right? If you remember, in that we have got all the components, right? The number of components of Riemann tensor is exactly the number of components that are free, right? After you use coordinate transformation. So Riemann tensor is the only one that with two derivatives of the matrix. Okay. So this is what you can get. This has four derivatives, right? This has two, this has two. So this is not, this can be there as a small correction, but this is not a dominant term. But there is no term involving a metric with one derivative, right? We saw that with single derivative, right? By coordinate transformation, you can just make the first derivative of the metric to 0, right? In the local inertial frame. And that means that there is no tensor that you can construct out of a single derivative of the metric. So two derivative is the minimum, right? So if Newton's laws had been one derivative, right? Then you will be in trouble. Right? So it's good that you have two derivatives. One derivative. Zero derivative term you could write, right? But then those are not there in the Newton's equation. Right? You can say, okay, you can write a zero derivative type very small coefficient, right? The cosmological constant is like that. Right? But we don't we try to see the minimal thing that we can do, right? No, R is just a scalar, right? Times G mu nu. Scalar curvature, exactly. Right? R is R rho sigma, G rho sigma. Because G mu nu is 0. Right? That's why you cannot get anything with first derivative of the matrix. But just G mu nu is okay, right? you could have added a small coefficient named G mu nu, right? And cosmological constant is exactly that term. So then we expect that G mu nu should be given by A times R mu nu plus B R G mu nu. And it has to satisfy this. So what is that quantity? You have seen it before? R mu nu minus, yes. So G mu nu must be proportional to R mu nu minus R by 2 G mu nu. Because we saw that using the Bianchi identity, this actually vanished, right? The d mu of this was 0. So as long as you accept that it's only two derivative action, yeah, the equation of motion contains only two derivatives, then the left hand side is fixed up to overall constant. Right? Overall constant, of course, you cannot determine by this argument, this kind of logic. Is it clear? Oh, because d mu of this is 0, and that's the only thing that satisfies this. If you take d mu of this equal to 0, right, then A and B basically get fixed. The ratio A by B get fixed, because you had seen earlier that this, if you look at the discussion on Bianchi identity, then you had found an identity like this. Okay? So this is a combination that has that property. Is it clear? Okay, so now let's look at the right hand side, H mu nu. So in Newton's equation, the right hand side was mass density. Okay. So that's the first information. The second information is that for consistency, this should be conserved. D mu H mu nu should be 0. Now in special relativity, okay, you don't even have to go to general relativity. In special relativity, mass is not conserved. Okay, mass is not conserved because when a radioactive atom decays, for example, radioactive nucleus decays, right? It converts some of the mass to energy. So mass is not conserved, but energy is conserved. Right? Energy is closely related to mass. Right? In fact, if the particle is at rest, then the energy is equal to mass, right? In the C equal to 1 over 8. Okay, the rest mass energy. But otherwise, energy is conserved in the process, right? Even the mass is not. So one might expect that, okay, the right hand side should involve energy density. Right? Because energy is at least conserved. So there is some hope that you'll get something like this. But energy is not a scalar. It's even in the just in special relativity, right? Forget about general relativity right now. In special relativity, energy is part of a 4 vector. So if energy enters, then all components must enter. Right? All components of momentum. So the best hope is that the right hand side will involve the appropriate densities and currents of energy and momentum. Is that clear? So this is going to generalize our J mu, right? For electromagnetism, right, there is only charge density and charge current. Now there will be energy density, momentum density, and then energy current and momentum current. Is that clear? So let me write the right hand side. On the right hand side, what we have is P mu nu. So mu is like the mu of J mu. And this nu tells us that nu equal to 0 corresponds to energy, and nu equal to I corresponds to momentum. Okay, so T00 will be energy density. T0I for I equal to 1 to 3 will be momentum density. Right? So Ti0 will be energy current, right? The analog of the Gi, okay, with charge replaced by energy. And Tij will be the analog of the momentum current, right? The, again, analog of Gi with charge replaced by momentum. Right? So this is the kind of structure we expect on the right hand side. Is this clear? Yeah, because you are trying to generalize mass. Newton's law tells us the right hand side is mass density, right? And you know the mass is not a good thing because mass is not constant, right? So the closest to mass in because d mu h mu nu equal to 0, right? For consistency, this has to vanish, right? So if it was really mass density, imagine that there is suddenly a radioactive decay, right? So when some mass gets converted to energy, then d mu h mu will not be 0 there, right? Because mass is not constant, right? But radio energy is constant, right? Even in radioactive decays, right? Total energy of the initial state and final state is the same. Okay, that's why we argued that the mass must be replaced by energy. But once you replace mass by energy, then you must also have the momentum, because energy and momentum are part of a 4 vector, right? You cannot just have energy and no momentum. So that's how we argued that this, instead of having just J mu, we must be having some T mu nu, right? Where nu equal to 0 corresponds to energy density and energy current, and nu equal to I corresponds to momentum density and momentum current. No, because T mu, as long as T mu is something whose for is d mu T mu equal to 0, right? It will be consistent equation. Right? Is that it will not be something that you will be familiar with, right? Okay, now come left hand side. You want d square of what? But it has to act on something, right? But the covariant derivative of G is 0, right? So that's why you cannot have the covariant derivative of G, right? So you are saying something like this, right? D rho G mu nu, right? But this is 0 because the covariant derivative of G is 0. Okay? That's why with two derivatives, the only thing that you can construct is Riemann tensor and its various derivatives, right? From Riemann tensor, we just take various contractions to get other things. Exactly, exactly. Is it clear so far? Okay. So now I'm going to write down an expression for T mu. Okay. So let me remind you that J mu was given by sum over n En. Okay, I'm going to write this in a slightly different way. Is clear? Oh, yeah, thank you. Yeah, I have to put that minus determinant G of x to the minus half, right? This I can take outside also. Doesn't matter. This one it doesn't matter where I write it, okay, but I write it this way. This charge current, J mu, right? So I want to construct T mu. So what should you do? We know how to construct charge currents. How do you construct T mu? Where is the information that this is a charge current? En is the charge, right? So I now want energy momentum current, right? So what should we do? So En I have to be replaced by momentum, right, of the nth particle, right? Because from charge current I'm going to momentum current, right? So all I have to do is that you replace En by momentum, right? So I can write this as sum over n integral dun mn this is new because it's a new is the one that is containing information about whether it's energy or momentum, right? So this is the momentum carried by the nth particle. Yeah, because for the momentum you have to use proper time, right? Okay, this you cannot change. Yeah, so that's what we'll do if you want to make it symmetric, right? This here it was all un, but un can be chosen arbitrarily, right? Tau n, this part has to be tau n because momentum is mn dx d tau, right? But un is up to us to choose. Right? Un is an arbitrary parameter, so we can choose un equal to tau n, right? We can just make it look better. Choose un equal to tau n. Yes, we do. I keep forgetting that minus determinant g of x to the minus half. So this is sum over n integral d tau n mn dxn mu d tau n but mu is not needed because it's 4 vector by yes, tau n at that point, right? Exactly. I mean, at a particular value of un, right? There is a tau n, right? That we have to reference with respect to that tau n. Yeah, but what I'm saying now is that the next step that un was completely up to us to choose, right? Un was just some arbitrary parameter that level the trajectory. So you might as well take to be tau n, take it as tau n. Right? The advantage is that now you can see that it's manifestly symmetric under mu nu exchange. Right? In this form, it was not completely clear. Right? But once you have written it this way, it's symmetric under mu nu exchange. And that is good because P mu nu better be symmetric, right? Because we had argued that the antisymmetric part will drop out of the equation anyway, right?
It seems like that RHS is a function of tau n. The second line it has some indication.
Yeah, because tau n actually is okay. It's not a function of un. That's what I said. This is tau n of un, right? Because on a trajectory, right? What's happening? That this is a trajectory labeled by u, right? At every point, the proper term takes some value, right? Proper term from the initial position. That's it. That is tau n. So tau n is actually a function of un.
That's our force velocity.
That's a force velocity, exactly. Right, and now all I'm saying is that in the second step, un I can replace by tau n, right? Because I can always say that we will parameterize this by the proper time along the trajectory. It makes no difference, right? Because there is a dun and dun. So when you replace by un by tau n, right, which is a function, they just cancel. The Jacobian that you get from here exactly cancels what you get from here. So this is then the expression for the energy momentum tensor. For a stream of particles that is moving. So let me now write down the final equation. So R mu nu minus half R G mu nu is equal to some constant times T mu nu. Yeah, I'll just write, you can always raise and lower index by geometry, right? So it doesn't matter whether you put it up or down.
Generally, if we have other fields like they would also have to be included.
Yes, and we'll see in a minute. Well, maybe, yeah, I'll try to do that, right? That they'll have to be included. But let me just say right now that the C is a constant, right? At this stage, C is not determined. Okay. So what determines C? Newtonian limit again, right? So you have to go to a Newtonian limit, right? So I'll leave it as an exercise. Go to the Newtonian limit and determine C. Not really. C should be proportional to Newton's constant, right? Because in Newtonian limit, the Laplacian, the divergence, yeah, del square V, right, is proportional to G times something. So C should certainly involve the Newton's constant, right? You have to figure out the 4 pi factors, etc., whatever factors, other factors are there in this. Okay. So Newtonian limit basically means left hand side, you know what Newtonian limit means, right? Weak field, static. Okay. On the right hand side, you must basically take these particles instead of assuming they are freely flowing particles, take them to static. Right? Take even one particle, placed at a point. Okay, that is a static particle, so and then you can compare the two sides, right? We know what Newton's laws should look like, that if you have a single particle placed at a point, what equation it satisfies, right? There's a delta function source, right? You compare that with what you get from here. Okay, now let me just say one thing. I think this I'll maybe do next time, that we have to check that this is 0. Right? I just wrote down something, but is it 0 or not? Okay. So this we can check in the local inertial frame. Because if it's 0 there, then it will be 0 in a general frame. It's a tensor equation. So remember how we proved this? Okay. We basically got something. It became sum over n ddu minus ddun of a delta function. Okay, and then we say that okay, we can just integrate parts, ignore the boundary terms, and it's 0. The analog of that here will be sum over n integral, okay, not n. This will be dd tau n. Let me write that first, because I have just changed the parameters from u to tau. But here will be mn right? because En is replaced by this, right, in this whole analysis. So if we just go through it, you will find that you arrive at something like this. But now you are in trouble, right? Because we cannot do integration by parts. New, thank you. New is the free index on the other side. We cannot do integration by parts, right? But we can, provided we let the derivative act on this. That will give you d2xn d tau n. This is all in prime frame, tau n square, right? That vanishes if this satisfies its equation of motion, right? Not otherwise. So we see that we have to use equation of motion for x to conclude that the energy momentum tensor is constant. Is that clear? Right? In the local inertial frame, it's free particle equation of motion. In the other frames, it will be some geodesic equation. Is it clear? Now you can ask the following question. Let's suppose that a particle is not free. I'm driving. There's an engine that is driving the particle. Right? It doesn't move along geodesic, right? In local inertial frame, it doesn't satisfy d2x d tau square equal to 0. So what happens in that case? An engine driving a particle cannot produce gravitational field. Yeah. So what this is basically saying is that whatever force is driving the engine, right? Doesn't matter whatever it is, right? It may be a nuclear engine, it might be an electromagnetic engine, right? Whatever is driving the particle, right, must produce its own energy momentum tensor. So the total energy momentum tensor of the particle plus the engine and everything has to be constant. And what goes in as a source of gravitational field is everything, right? Not just the particle, right? But also all the forces that the engine is acting on it, right? They will have their own energy momentum tensor. It's like electromagnetic field. If it was driving the particle by an electromagnetic field, right? Electromagnetic field will have its own energy momentum tensor. And all that will act on the appear as the source of gravitational field. So the total energy momentum tensor is always constant. Right? That is the only thing that you can put on the right hand side of Einstein's equation. Right? You cannot just choose some part of the energy momentum tensor and say, okay, these are the ones which source gravity, and others don't. Right? Every component of the energy momentum tensor, whether it's coming from a particle or a field, right, has to be included as the source. So next time we'll try to work out the electromagnetic energy momentum tensor, right, just from this kind of argument. Yes.
It's a total geometric element, whereas the edge on the right hand, it can we have made force that it has to satisfy Newton's law under certain level. But here we are choosing Newton's law as a stop gravity. But any force and any equation of satisfy Newton's second.
But we are replacing that by the relativistic laws, right? See, the gravity has, so it's a postulate that the effect of gravity is determined by curvature of space-time, right? These equations that we are discussing today tells you how to determine the curvature of space-time in terms of the particle sources or in terms of sources, right? The fact that these describe gravity, of course, is an experimental fact, right? These other forces are different variables, right? If you want to couple gravity to electromagnetism, for example, electromagnetic field will be given by F mu nu or A mu, and gravitational field will be given by G mu, right? So the combined theory of gravity and electromagnetism will be a theory which has both G mu nu and A mu, right? Because G mu nu describes only the gravitational part of the fields. Yes.
The right hand side can include the effect of.
Yes.
So, and that is affecting the metric.
Yes.
And in the postulate itself, the metric is related to gravity. So, for example, is it something saying like everything is gravity?
No. Gravity is being sourced by that, right? The fact that it is being sourced by that doesn't mean that that object is gravity. That object has other effects also, right? See, gravitational part is gravity is only sensitive to the energy momentum tensor. But the same energy momentum tensor may be produced by one configuration of electromagnetic field or a different configuration of electromagnetic field, right? They affect charge particle motion in different ways, even though the gravitational energy momentum tensor is the same, right?
For example, if you have some TV and this TV is related to the evolution of
T produces evolution of the matrix. T is a source, right? But the source itself may have its own dynamics. Okay, you can forget about gravity. First, think of electromagnetism, right? Electromagnetism has electromagnetic field that has one set of variables, but it also has other set of variables which are producing the electromagnetic field, right? The charges and their motion. They are not the same thing. Their equations are coupled, right? But you have to describe the full configuration, you have to take electromagnetic field as well as the charges, the degree of freedom or the charge particles as independent degrees of freedom.
I know the electromagnetic fields, and then just by putting at this in this equation, I can find out what is the equation for what the particle trajectory.
If you know the
if I know the TV,
yes, you know how the particle trajectory will be. Yes.
So it is something like, for example.
But that's like if you have a charge particle, right? And if you have electromagnetic field, forget about gravity, then you know how the charge particle trajectory will be, right? But that doesn't mean the charge particle is the same as electromagnetic field, right?
Have a freedom of choosing what edge to use. So, like here we are considering that under certain limit you have Newtonian. Is it necessary? There can be some forces that might not be Newtonian.
Yeah, that is true. There are certainly forces that can be non-Newtonian, right? Electromagnetic field, for example, it has a Newtonian limit of the electromagnetic field, right? But at least for the forces, for the sources where we do have Newtonian limit, it should reproduce the answer. But it has to be conserved, right? And yeah, if you can find another conserved h mu nu, right, that's good enough, right? You can couple gravity to that. Then what will happen is that you will declare that as the energy momentum tensor. Right? That will be one way of defining energy momentum. Because how do you, for example, assign energy momentum tensor to electromagnetic field? Right? We know that if we don't assign energy momentum to electromagnetic field, the charge particle energy is not conserved, right? So it's the sum of the two that is conserved, right? If you had found another expression involving electromagnetic field, so that the sum of the particle energy and that is conserved, that is also good enough, right? Well, it's not unique because you can certainly add higher derivative transfer terms with 4 derivatives, which has this property that d mu g mu nu equal to 0. You could add that, right? As long as the coefficient is sufficiently small, so that the Newtonian limit, that effect goes away, you are allowed to do that. That all you have to make sure is that the Newtonian limit is reproduced correctly, because you are trying to produce get a theory which in appropriate limit gives Newton's gravity. Yeah, if you allow only second order derivative, then the left hand side is unique, right? There's not much you can do, because that we saw, right? Because r mu nu and r g mu nu, right? You can also add, okay, you can add constant times g mu nu, right? That's no derivative. That you can add, and that's what we call the cosmological constant. But otherwise, there is not much choice in this.
Adding a cosmological constant will not violate the d mu, right?
No, because d mu g mu nu is identically 0, right?
On the right hand side, the d mu that we have, some kind of Euler current
Well, the point is, because general coordinate transformation is a local transformation, right? There is no northern current for that. You can say it's a northern current in when there's no gravity, when you switch off gravity, right? Then there's a global symmetry, the Lorentz symmetry. It's the northern current of that. Yeah, it does, but the physics is slightly different here. Right? This is a local current conservation. This is more than current conservation, right? Because this is saying that locally there is a current which, well, maybe okay. If in a local field theory you can define local current conservation as a global symmetry, right? But this is somehow different from that, right? Because here we are getting this from consistency of the gauge theory, right? You can say, okay, at the end it gives something that looks like an Noether current, right? But if you follow the standard Noether procedure, right, for a local symmetry, you will not get this. Yeah, I mean the point is you expect that in any quantum theory, right? Effectively, we will get higher derivatives of G, right? Except that the coefficients are so small that it's not observable, right? So, certainly, to this date, I mean nobody has observed any effect other than hot air wrote down, right? Yeah, cosmological constant has been observed, right? So lambda is non-zero, you know, right? So the actual equation will be that there should be a term here which is okay. Sometimes one just takes it to the other side and puts it inside T mu, right? But yeah, so there is such a term that has been observed. It can be a scalar field, right? But as far as we know today, if it has a scalar field, then it would be natural to take it out on the other side, right? Because anything that depends, it depends on other fields you are putting on the right hand side, right? But so far, right, we don't know if it's a scalar field or not. I mean, it's consistent with it being a constant. Whether this is true or not. Yeah, and I'm saying that you can, one way to check this is to check that in the local inertial term this is true, right? Then I applied the same argument that we gave last time, right? For this, we got a total derivative. If you apply the same argument, you will arrive at a term like this. En will be replaced by mn dx prime dt of n, and then there will be something like this. And now the point is, this is not zero identically, because in order to make this vanish, you have to do the integration by parts, and this dd tau n will act on this, right? So you have to use the equation of motion for x prime to show that this is zero, right? Unlike in this case, right? Here it was a zero because n is constant, right? If we had postulated that n itself can change as a function of time, then we'll have the same problem there, right? But normally, when you do Maxwell's electrodynamics, en is just a constant, right? Once you fix the charge of a particle, it just carries the same charge.
How did it motivate that discussion about the particle being driven by an engine?
Because if a particle was being driven by an engine, then this would not be true, right? d2x prime d tau square is not zero, right? Then there is an inconsistency, right? And the way this inconsistency is resolved, that you also have to take into account the contribution of the energy momentum tensor due to the engine or whatever forces are driving the engine, right? I mean, if the engine is in electromagnetic field that is driving the particle, right? It doesn't have an engine. Suppose there is electromagnetic field present, right? Where this is not zero, right? You saw that there is a right hand side of this equation, right? The Lorentz force law. So that can be compensated if you take into account the energy momentum tensor of the electron. If you use the standard Noether procedure, you will just get zero. Yeah, because the systematic way of doing the Noether current, right, is to say that you take a variation with some parameter, right, and then you make the parameter x dependent on x. Okay, then the symmetry is no longer a genuine symmetry. If it is a global symmetry to start with, you make the parameter x depend on x, right? It's not a genuine symmetry now, so there will be a term left over, right? And the leftover term will be of the form integral of whatever the symmetry transformation parameter, okay, times something, right? Okay. And then this J mu is a conserved current. right? Because under local symmetry, it's not zero, but it has to be proportional to the derivative of epsilon times j mu, because for epsilon equal to constant, it should vanish, the variation of the action. So this j mu is a conserved current, right? For a gauge symmetry, it's zero even when epsilon depends on x, right? So you don't get term like this. So that procedure breaks down when there is a local symmetry, because the procedure for deriving Noether charge, right? At least one, the systematic procedure is that you take a variation and make that depend on x, right? So that it doesn't remain a symmetry. And then how much it violates, how much the action changes, contains information about the current. But if the local symmetry is a genuine symmetry, right, then you will get j mu equal to 0, right? Because the variation will be identical to 0. So
in this case, it's a genuine symmetry.
In this case, a genuine symmetry, exactly.
This kind of statement has to be true for arbitrary epsilon, right?
Exactly.
So genuine.
Exactly.
You said that equation of motion has to be satisfied in order for it to be conserved.
Yes.
So if your particle was driven by some force, then what would happen? Then this would be true.
Then the equation of motion, you still have to use it, right? Then d2x d tau square will be given by that force, right? So that something has to cancel that, right? And now the idea is that there will be an energy momentum tensor of that field, right, which is producing the motion, right? Its divergence has to be calculated.
And
that will cancel this term.
That
Whole thing will be conserved. So that's why gravity, coupling gravity to something is hard unless that something is a fully consistent field, right? That you have to make sure that you are taking into account total energy momentum tensor, right? And that has to be conserved, right? You cannot simply say that we have a force driving a particle, right? And we'll study gravity produced by that particle and not take into account that force, right? You'll never be able to solve the equations in such cases, right? You have to look at the gravitational field produced by the particle and whatever mechanism is driving the particle. All those forces, exactly. Yes, right. So that's why typically one way to define those energy momentum tensor is that if you have an action, right, then you vary the second term of the action with respect to g mu nu, and whatever comes, whatever multiplies that analog of the h mu nu, you declare as the energy momentum tensor of the other forces and fields. Right. So this, instead of using Noether procedure, right, this is one way of defining the energy momentum tensor of the particle of fields. Right. Just look at its coupling to gravity, right, and whatever you get as the coefficient of delta g mu nu, you declare that is the energy momentum tensor.
Class in the Newtonian limit, we introduced potential energy as how it's got is done by calculation. But now when we come to GR, it is like just a component of it. So how will we identify the potential energy physically? It's just as a component.
Yeah, there is a way to do that in the weak field limit, right? Where basically this is a nonlinear equation, right? This r mu nu minus half r g mu nu. You can just take the linear part of this, and then everything else you took on the right hand side, right? So then that will give an energy contribution to the energy momentum tensor due to gravity, right? It's an artificial construction because it works only in the weak field limit, right? That's the way you can also define gravitational energy momentum tensor. This we'll discuss near the end of the course, maybe, right? How to define the energy momentum tensor of gravity, right? This is the analog of the gravitational potential energy. So because by this argument, right, the gravitational potential energy should also source gravity. Sounds strange, right? And that the way to explain that is a weak field concept, that the gravitational potential energy. So you have to reorganize this as putting some linear terms on the left hand side and all the nonlinear terms on the right hand side. And those nonlinear terms you can reinterpret as the gravitational potential energy. Yeah.
Just related to this only. Some energy movements. That is related to what we can analyze this approach and we say that gravity determines how the plate vector.
Yes, but that is not the same statement as saying that gravity is determines all the other things. Right?
Can I say that this now gravity's identity lies in the metric?
Yes, exactly.
And metric is determined by all sort of energy movement, etc.
Exactly.
Can I just combine